Minashi, done?
Yes, sir.
So this is all about the entire chapter, thermal properties of matter. Next is thermodynamics. First, let me define you what do you mean by thermodynamics. Therm and dynamics. Therm means heat, dynamics, flow. So you'll say the study of flow of heat or conversion of heat from one form to some other form, like in case of electrical term, in term of mechanical, and some other form as well. So it is the study of flow of heat from one point to another, and also conversion of heat into other form of energy. So in this part, first we define what do you mean by thermodynamical variable. All the different physical quantity such as number of moles, pressure, volume, temperature, which may define condition of gas at instant, or you'll say the physical quantity on which the condition of gas may depend upon are termed as thermodynamical variable. So the physical quantity on which condition of gas depends upon are termed as thermodynamical variable. So if we have to relate in these thermodynamical variable to define the condition or state of a particular gas at any instant, it will be termed as equation of state. I'm just defining some of the term which is used in this whole chapter. So you must aware about of these terms. So equation of state is the relationship between different thermodynamical variable which defines the condition of gas at any instant. So in general, it will be P V raised to X is equals to some constant. In some other term, it will be P to the power 1 by X, V is equals to constant. In some other term, or in terms of ideal gas, it will be PV is equals to nRT. So all different equation of state for any different processes will be in the form of only these three different conditions. Raza, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
You are done?
Yes.
Yusra, any doubt?
No, sir.
Now the next term is molar specific heat constant, which I have already defined in last chapter in terms of heat capacity, specific capacity, and similarly molar specific capacity. It simply states the amount of heat is required to reach temperature of 1 mole of gas by 1 Kelvin or 1 degree Celsius at given condition or at given different processes. So it is the amount of heat is required to raise the temperature of 1 mole gas by 1 Kelvin or 1 degree Celsius at given condition or process, thermodynamical processes. So it will be general formula of this relation will be, you may write dq equals to nc dt, where c is called molar specific constant. So general formula of this c will be r divided by gamma minus 1 minus r minus x minus 1, where x is same variable which is also in the case of equation of state. So first, try to find the value of x from this equation of state, put it in this part. You will get molar specific constant related to that process easily. So this will be generalized formula of calculating molar specific heat. In this part, let me define you the term which is used. First, R, which is also called universal gas constant. It is equals to 25 by 3 or 8.314 joule per mole per Kelvin. Next, gamma. Let me define what you mean by gamma. To define this gamma, let me explain you what do you mean by degree of freedom. Degree of freedom is all the coordinate or direction in which a particle of gas may contain energy due to its motion. So all different direction or variable along which a gas molecule or particle may contain energy is termed as degree of freedom. So it is the direction along which a gaseous particle may have energy. So let me define you its different behavior. Suppose you have any monoatomic particle, any diatomic particle. Let me define first for monoatomic particle. This monoatomic particle will tend to move along x-axis, y-axis, z-axis. So it will have translational motion along all these different coordinate system. So this particle, monoatomic particle, will have translational energy due to going along x-axis, due to y-axis, as well as z-axis. So how many directions in which this monoatomic particle will have energy contained in it? So we will say in 3 different directions, and all these direction is due to its translational motion. So we can say total number of degree of freedom for monoatomic particle will be 3, and all are due to its translational motion. Mazia, is it clear? Nabila, any doubt?
No doubts.
Try to find the number of ways in which this diatomic particle will have energy. This diatomic particle may tend to go along x-axis, translational motion, along y-axis, translational motion, along z-axis, translational motion. Suppose you have diatomic particle like this. So it may tend to go along this axis, x, y, or z. So it will have all 3 different translational motion. Next, whether it can rotate or not. So you'll say, this is diatomic. It can rotate along this axis. It can rotate along this axis as well, but there will be no rotation possible along this axis, its own axis. So there will be rotation along this axis and also along this axis. So just count how many different ways along which this diatomic particle have energy contained in it.
Five, sir.
Good. Raza, is it clear how it is 5?
Yes, sir.
It's 3 due to its translational motion and 2 due to its rotational motion. So in total, it will have 5 different ways of energy containing in case of diatomic. Now let me ask for water molecule. First, anyone just tell me what will be the shape of water molecule?
So bend-shaped tetrahedral.
Good. V-shaped. Like this. Due to lone pair on oxygen, which tends to bend its shape. Let's say this is z-axis, this is y and z. Now try to find how many ways this molecule will tend to acquire energy due to translational and due to rotational both. First, you will say it will have translational energy along all 3 different coordinate axes. and it will rotate along this axis as well as this axis and as well as this axis. So it will have 3 translational motion and 3 rotational motion. So in total, 3 translational, 3 rotational. So it will be total of 6 different ways of energy containing.
Sir, how
Nabila?
do we judge that it rotates or not, sir? Like which axis rotates?
Okay, just 1 minute. Suppose in the case of diatomic, try to see along this axis. Will there be any rotation possible along this axis or not? You will say yes, it may rotate along this way. But if you see along this axis, it will behaving as point object from this part. And for point object, there will be no rotation possible. Okay.
Yes, sir.
That's why we may define for diatomic, we have only 2 rotation possible, but for triatomic, for bend shape, we have 3 different rotation possible. Okay.
Okay, sir.
Nabila, any doubt in this entire part, degree of freedom?
No, sir.
Now, on the basis of this degree of freedom, if someone asks you whether this particular degree of freedom depend upon temperature or not, so you will say in case of monatomic, it will remain same, but in case of diatomic, triatomic, on increasing temperature, it will tend to decrease the strength of bond in between them. So there will be loosening of bond, which tends to increase their vibrational energy. So on increasing temperature, vibrational energy of particle, diatomic, triatomic, polyatomic, increases, so degree of freedom increases. Krishna, is it clear?
Yes, sir.
So just 1 minute. On increasing temperature, due to weakening of bond, vibrational energy of molecule increases, hence degree of freedom increases. Just write it down till this part first.
Chup. Sir, so the third one is triatomic.
Yes,
Okay.
this is a case of water molecule. If you will be asked to define for carbon dioxide, it will be linear in shape. So it will behave as of same degree of freedom as of diatomic molecule. Okay. So depending upon the shape of molecule, we may define its degree of freedom.
Sir, can you please scroll down?
Done, sir.
Done, sir.
Raza, done?
Yes, sir.
Now, related to this degree of freedom, let me define you what do you mean by gamma. Specific gas ratio, which is gamma. So it is equals to Cp by Cv. I will define you later what do you mean by Cp and Cv. C is molar specific heat constant and P is for constant pressure. C is molar specific heat and V is for constant volume. So these are two molar specific heat for two different processes. And it will be equals to 1 plus 2 by F. So if you put the value of F related to monoatomic, diatomic, triatomic, you will get gamma for monoatomic 1 plus 2 by 3. So it will become 5 by 3, 1.67. In case of diatomic, F is 5. So you'll get 7 by 5, 1.4. In case of triatomic, 1 plus 2 by 6. So it will be 1 plus 1 by 3, 4 by 3, 1.3. Now just try to compare these different specific gas ratio. So you get monoatomic will have maximum gamma and triatomic will have minimum gamma, since gamma is inversely proportional to degree of freedom. So may relate according to this, gamma for monoatomic maximum, then diatomic, then triatomic, and this will be less than 2, greater than 1. So the range of gamma will lie in between this part. Nabila, is it clear?
Yes, sir.
So these are some basic terms related to this thermodynamic variable. Just write it down, this part.
Done, sir.
Done, sir.
Okay. Next term is, what do you mean by ideal gas and real gas? Suppose for a gaseous particle, this and this, if there is interaction between these two particles, interaction due to intermolecular force of attraction between them. So if there is interaction between particle of gas, this particular gas will have some potential energy due to interaction. And also, due to temperature, it will have some thermal kinetic energy. So, on adding these two energy, in case of gas, it will be termed as internal energy. So if someone asks you, what do you mean by internal energy of a gas? So you'll say the total sum of potential and kinetic energy for a gas is termed as internal energy. So it will be kinetic energy plus potential energy. Now suppose ideal gas. It says if there is no interaction between particle of gas, if there is no interaction between particle of gas, so there will be no potential energy in case of ideal gas. So it will have only kinetic energy due to temperature. So on adding to get total internal energy in this system, it will be only due to kinetic energy. Is it clear? What is the main difference between ideal gas and real gas?
Yes, sir.
Yes, sir.
Raza, any doubt?
No, sir.
Now, we have to define on what condition this real gas will tend to behave as ideal. So you'll say there should have no interaction between particles. So on what factor the interaction between particles may depend upon? So you'll say the separation between them. The smaller the separation between particles, it will have a stronger force of attraction between them. So if you somehow tend to increase the separation between particles, interaction between them decreases, and hence it will tend to behave as ideal gas. Is it clear?
Yes, sir.
Yes, sir.
In class 9th, you must have learned about an experiment. Suppose in a piston, cylindrical piston like this, there are n number of particles, this, and so on, like in case of gas. So if you compress it a little more, the crowdness of particle will start increasing. If you further compress it, the crowdness of particle further increases. So what I'm doing here, I'm just increasing pressure of this particular system. So you will say on increasing pressure, separation between particle decreases. So interaction between them increases. So what if I will decrease pressure of this particular system? So separation between particle increases. So first criteria for this interaction to be decreasing, decrease the pressure of this particular system. And next, even that, they will have some interaction between them. So increase the temperature of this particular system. So it will have some more thermal kinetic energy. So it will tend to vibrate in a random direction. So there will be least interaction, or there will be no interaction at that case. So we can conclude at low pressure and high temperature, real gas tends to behave as ideal gas. Is it clear?
Yes, sir.
Yes, sir.
Nabila, any doubt?
No, sir.
So at low temperature, low pressure, and high temperature, real gas tend to behave as ideal. Just write it down. Minashi, any doubt?
No, sir.
Done, sir.
Yusra, done?
Yes, sir.
Okay. Next concept is, what do you mean by system and surrounding? Suppose in a vessel, enclosed by a piston, and there is gas, which is under observation, for which we have to calculate work done, heat supplied, ejected, internal energy, and different physical parameters related to this thermodynamics or thermodynamical variable. So the gas which is under observation is termed as system, and this is the all influencing factor outside of this particular system is termed as surrounding. And the combination of these two parts is called universe. System is the gas enclosed in vessel which is under observation. Is termed as system, and so the all influencing factor to this particular system is termed as surrounding. All other influencing factor which can affect this particular system by any means is termed as surrounding, and the combination of system and surrounding is called universe. Is it clear?
Yes, sir.
Yes, sir.
Now, on the basis of interaction of system to its surrounding, we may divide this system into three different parts. So next is types of system. First is open system. Second is closed system. And third is isolated system. So open system, a system which may allow exchange of both heat, means energy, as well as matter. A system which allows exchange of energy and matter, both between system and surrounding. So it will be termed as open system. Next, closed, a system which allows exchange of energy only. There will be no exchange of matter. Isolated, a system which restricts any exchange between system and surrounding, which restricts the exchange either of energy or matter between system and surrounding. Mazia, any doubt? Okay, just write it down.
Done, sir.
Done, sir.
Nabila, done?
Yes, sir.
Okay. So let's stop here for today. Do you have any doubt to any one of you till this part and this particular chapter?
No, sir.
No, sir.
Okay, this is all introductory part of this whole chapter. From next class, we'll start with processes and its various other terms. Okay. Okay, then
Yes, sir.
we'll continue next class.
Thank you, sir.
Thank you.
Thank